In least squares regression approach, we choose coefficients that minimizes the sum of squares of the errors. Let's try to understand these things through visualization. We learned in the previous slide, since y is the sum of the constants and the normally distributed error, y is also normally distributed at any given level of x. For example, if x equals x in simple x1, then y has a normal distribution with mean beta naught plus beta 1 x1. The variance of y is sigma squared. Similarly, when x equals x2, y has a normal distribution with mean beta naught plus beta 1 x2. Here is the normal distribution. When x equals x3, y values have a normal distribution with mean beta naught plus beta 1 x3. Note that all distributions have the same variance, which we refer to as sigma squared. The variance of y sigma squared determines the amount of variability or noise in the observations y. When sigma squared is small, the values of y will fall close to the line. When sigma squared is large, the observations of y may deviate considerably from the line. The true regression line goes through the means of these distributions. It is expected value of y given x equals xi, which is equals to beta naught plus beta 1 xi. This equation is represented through this red line. You can see this line goes through the means of these distributions. This is called the true regression line or the population regression line. The actual observations are on the distribution around the mean. The blue dots, the actual observations. Each observed point is on its own normal distribution with the center of the distribution, that is the mean yi, falling on the line. This sample point can be written as yi beta naught plus beta 1 x2, that is this value, plus the error term epsilon I. Epsilon I is the error term. Likewise, each observation has an associated error term. Let's move to the next slide. Same figure, I just removed the normal distributions from the diagram. This is the true regression line. And this is an observed value. This is equals to the mean of the distribution plus the error term. In linear regression analysis, we make several assumptions. The relationship between the response y and the regressors is linear. The error term has zero mean. The error term has constant variance sigma squared. The errors are uncorrelated and the errors are normally distributed. Taking together assumptions, the errors are uncorrelated and errors are normally distributed implies that errors are independent random variables. Usually, we don't have data corresponds to all individuals in the population. Instead, we get a sample of values like this. a subset from the population. The objective of regression analysis is to estimate the unknown parameters in the regression model using the sample data. This process is also called fitting a model to the data. Now suppose you have a sample of points like this. We want to estimate beta naught and beta 1. In other words, we want to estimate intercept and slope of the regression line. Intercept and slope of the population regression line. In other words, by using these sample points, we want to estimate beta naught and beta 1. To estimate intercept and slope of the population regression line, we need to draw a suitable regression line to represent the data. For that, we can draw a line like this, or like this, maybe like this. The question is, which line is the best? There are several parameter estimation techniques. We will be using least squares approach to estimate the parameters, or the beta naught and beta 1. The reason is the least squares estimators are the best linear unbiased estimators, where best implies minimum variance. Oh, sorry. Before moving to the next section, I would like to introduce another term, that's residuals. Distinction between the term errors and residuals is important. Error is the difference between the observed value and the true value. So, suppose this is your true regression line. Actually, we don't know. We can't draw it like this. Just for explanation, I draw this line using light red color and some dash marks on it. Suppose this is your true regression line, and this is your observed value. And the difference between this true value and the observed value is called the error. The residual is the difference between the fitted value and the observed value. Suppose this one here is y hat beta naught plus beta 1 x. Beta naught hat and beta 1 hat are the estimates of the beta naught and beta 1 that we calculated based on sample data using the least squares regression approach. This is called the fitted regression line. The difference between the fitted value and the observed value is called the residuals. The difference between the true value and the observed value is called the error. This distinction is important. Errors are unobservable, but residuals are observable. In other words, error term is a theoretical concept that can never be observed. But the residual is an observed value calculated based on the observed data and fitted regression model. On the other hand, a residual is an observed estimate of the unobservable statistical error. We make a few assumptions regarding the errors. We use residuals to check the validity of those assumptions regarding the error.